All right, so now moving on to the next part of this unit, which is going to be section 6b, and we're going to learn about radical expressions. So what you will need to know by the end of this video is how to read and interpret a radical expression. So what is it that we're actually trying to solve for, and what do the different parts of the radical expression mean? And then you're going to have to know how to simplify radical expressions that are what are called perfect squares. And then you're going to have to also know how to simplify radical expressions that are not perfect squares. All right, so those are the three things that you'll need to be able to know by this video. And remember, it's not about mastery at the end of this video. It's taking good notes and then being able to have those notes to help us apply to answer questions and practice so that we do eventually become mastered. All right, so let's first go ahead and talk about how to read and interpret what a radical expression even is. All right, so first, when you see this symbol here, that is the radical symbol. And that is telling us that we are now dealing with either a radical expression or maybe an equation if it's set equal to something. So once we see that symbol, this symbol is telling us that it is a radical. And within this symbol, there are different things that will be written that we need to understand what they are. So anything that's written inside of that radical, that is referred to as our radicand. And sometimes it can just be a number, and sometimes it can also be a variable. I can write x plus 2 inside of this. The entire x plus 2 will be considered our radicand. So anything that's written inside of it is considered our radicand. All right. Now, inside this little corner here, if you want to call it that, there will sometimes be written a number, or sometimes there's not a number written. But this is referred to as our index. When there's no number written, it's understood to be a 2. So if I don't write anything, then it's understood to be a 2 there. And what we're actually doing is taking the square root of that number. If there's a 3 written, then that will be considered our cube root. So that is our cube root. If there's a 4 written there, that is our fourth root that we're looking for. So that number there is telling us what root we're trying to take or what root we're trying to look at. And the entire thing itself is just referred to as a radical. So when we look at this as this one big problem, we can talk about it as a radical. All right. But what you need to know is the number that's on the inside of our square root or of our radical is referred to as our radicand. That this number here that gets written in our corner is referred to as our index, and it's telling us what root we're taking. And that whenever we see this symbol, that this is going to mean that it is a square root. Now, what is a square root? What is a cubed root? What is a radical? And as we know about inverse operations, that multiplying, so if I do 2 times 5, this is equal to 10, that when I divide, that is undoing what I did because they're inverse operations, and it brings me back to my starting number. We learned about inverse operations with multiplying, division, and also with addition and subtraction. So if I do 2 plus 5, I can subtract that 5 and get back to my starting number. Well, the inverse operation of a square is our square root. So if I say, well, what is 2 squared equal to? And that's equal to 4. I can then take the square root of that 4 and get back to the 2. So what this root is telling us is when we take the cubed root of let's say the cubed root of 27, this is saying, well, what number raised to the third power is equal to 27? If I say the fourth root of 16, this is telling us what number raised to the fourth power is equal to 16. So that index is telling us how many times we were multiplying some unknown number together to get us to our radicand. So in this case, since there's no number written there, we are understanding and say, well, what number raised to the second power, because it's understood to be a 2, is equal to 4. So that index is telling us how many times we were raising that radicand, or if we're referring to it when it's an exponent, our base, how many times we're raising that number or multiplying that number to get to this radicand. All right, so it's undoing the exponent. So if I were to say 2 cubed, well, that's equal to 8. Well, the cubed root of 8 is equal to 2. So anytime that this power and this index match, they undo each other, they cancel each other out, and they are our inverse operations. So you see, we started with the 2, and we ended with the 2 in both of these examples. All right, so that's what we're saying. When we're taking a cubed root of a number, we're saying, well, what number times itself 3 times gave us this radicand? When we're taking a fourth root of a number, well, what number times itself four times gave us this radicand of 16? All right, so that root is telling us how many times we're multiplying that number together. And the square root and the square of a number, they undo each other. They're inverse operations, just like our multiplying and division and our addition and subtraction. All right, so what you need to be able to understand, though, from this is that when we're referring to a radicand, we're referring to the number or expression that's inside of the radical symbol. And when we're referring to the index, it's the number that's written in that little corner, really small. So you cannot write this and say that that's the cubed root of 27. You must write it small like this here, because this is actually, when it's written big, it's saying 3 times the square root of 27. That's how we would read and interpret that. So make sure that you are writing it small and in that little corner there, so that way we know that this is our index or the root that we are taking. All right? So that's just being able to read and interpret a radical. The only ones that we're going to focus on mainly here are the square roots. All right, so when there's nothing written in that corner, we're focused on just the square roots in this year. But in the years to come, you will need to know how to do a cubed root and a fourth root and so on. All right, so now we're going to just start talking about perfect squares first and how we can take the square root of a perfect square. All right, so when we're simplifying what are called perfect squares, what that means is that when we take the square root of a number, it gives us a whole number and nothing else. So we get a whole number in return. So it means that there is a number that we square to get to that 4, or we square to get to that 16. So when we take the square root, it doesn't give us a decimal. It doesn't give us a number that, like, say, 2 times the square root of 2. It doesn't give us something like this. It gives us just a whole number in return. So think about what we talked about before. When there's no number written in that corner, we know it has an index of 2, or we're taking the square root of a number, or what we're asking ourselves is what number squared was equal to 4? And we know that in this case, 2 squared gives us 4. So this is considered a perfect square because when we take the square root of 4, it gives us a whole number in return. Same thing. If I say, what is the square root of 9? Well, the way that we're asking ourselves is until we get really comfortable and we just kind of can identify these and answer them very quickly, we're asking ourselves, so, well, since the index is 2, what number squared is equal to 9? And hopefully you are able to identify that 3 squared is equal to 9. So it gives us a whole number in return. So these are perfect squares, not the 2 and 3. When I say perfect squares, what I mean is actually the radicand. 4 is a perfect square because it gives us a whole number as an answer. 9 is a perfect square because it gives us a whole number as an answer. Same thing. If I say the square root of 16, well, once again, is 16 a perfect square? Can we rewrite, or can we say what number squared gives us 16? And yes, 4 squared gives me 16, so 16 is a perfect square. And our answer is 4. All right, so in our next part, I'm going to go through all these perfect squares that you're going to not necessarily have to memorize, but that hopefully through time and practice, we're able to easily identify. All right, so the number, the perfect square, is the number that we're actually taking the square root of. And if it gives us a whole number in return, then we would say that 16 is a perfect square, and that 4 is a perfect square, and that 9 is a perfect square. But what if I said, what is the square root of 3? Well, 3 doesn't give us a whole number in return. If we actually were to plug this into a calculator, it probably will give us something like 1.8 or 1.9 maybe. So maybe 1.8 if you plug that into a calculator. So you see, it doesn't give us a whole number as a answer. So 3 is not a perfect square. It must give us a whole number as an answer. All right, so that is what a perfect square is. And those are the ones that we're actually hoping for when we get radicals, because it just makes our life a lot easier. It's not hard problems. It's not anything that we really have to think about. All right, and then the other thing I want to talk about before we move on to anything else is when I give you this square root, what a lot of people want to do, well, the square root of 25, once again, can I rewrite, or is there some number raised to the second power that equals 25? And yes, that's 5. What some people want to do when they're writing their answers, they want to write it as the square root of 5. That is not how we do it. We can think of that square root as an operation. So just like we would never write 5 times 2 is equal to 10 times 2, we perform the operation of times 2. So we wouldn't write it again. Our answer is just 10. When we take the square root or the cube root or the fourth root of a number, we took it already. It no longer exists. We simplified it, and that root isn't there anymore. So we would just write it as 5 and not the square root of 5. There are times, as we're going to go through really soon, where we will need to keep a number under the radical because it's not a perfect square, and we couldn't completely pull it out. So there are times where the radical will exist, but that's when we couldn't take it for the number. All right, but when we actually take it, it is an operation. It no longer is written there. So the square root of 25 is 5, not the square root of 5. Because if we were to try to take the square root of 5, this probably is equal to maybe 2.1 or 2.2, I would say. Probably 2.2, approximately. So this does not equal 5, which is what we're saying our answer is. So when we take the radical or the square root of a number and we actually took it, we don't write it anymore. All right, so it's just the whole number that we have taken out. All right, and then when we go through simplifying, you'll see there's sometimes where we can't take the square root of a number and sometimes that we can. All right, so perfect squares are numbers that when we take the square root or cube root or whatever root we're taking, it gives us a whole number in return. If it doesn't give us a whole number in return, it is not a perfect square. All right, so now let's go ahead, and there's a chart that I'm going to have you fill out of all of our perfect squares that you're going to have to be able to identify, and then we're going to use that to simplify and solve for numbers that are not perfect squares. All right, so this is a chart and a table that you're going to fill out in class as well. So you're going to fill this out in class, have this in your notes. Writing this down will only help us to remember this even more. All right, and this is something that you're going to be using as what we're doing next, which is simplifying radicals that are not perfect squares. All right, so all of our perfect squares are these x squares. So all these numbers here, when I refer to as a perfect square, these are our perfect squares because I can take the square root of all of these. The square root of 4 is equal to 2. The square root of 9 is equal to 3. The square root of 16 is equal to 4. So you see, the way that this chart is written is we have x, which is just representing some number, and then we have x squared. So we're taking that number and squaring it. And since we know that any number squared, when we take the square root of that number, that they're inverse operations, it starts back to our original number, that all of these numbers are perfect squares. And all of these numbers, when we take the square root, is just going to give us back our original number x that we started with. So the square root of 36 is 6. The square root of 49 is 7. The square root of 64 is 8. The square root of 81 is 9. The square root of 100 is 10. The square root of 121 is 11, and so on. All right, so what you have to identify in this chart is all of these numbers that I highlighted are our perfect squares. Those are the numbers that we can take a square root of. I can't take the square root of 2 and give me a whole number in return. All right, so these are all my perfect squares. And then when I take the square root of that number, these are the answers that we get. The square root of 4 is 2. The square root of 9 is 3, and so on. All right, that's what you need to identify with this chart. And we're going to use this to answer these next questions. All right, so it's really, really, really important that you understand what this chart is telling us. The x squares are all of our perfect squares. It's taking the number and then just squaring it. And these are the numbers, the ones highlighted in yellow, that you will have to be able to identify easily. All right, so now let's go ahead and start simplifying numbers that are not perfect squares. All right, so now, just like we have to simplify everything that we do, if I gave you the fraction of 10 over 8, you don't leave it as 10 over 8. You would reduce this to say it's 5 over 4. We simplify. We always simplify everything in math. And that is the same case with our radicals, because we're going to learn something you'll learn something in the future in Algebra 2 and possibly in geometry, where you will have to add radicals together. And if you can't reduce your radical to its most simplified form, you're not going to know that we can actually add them together. You're going to think that they can't be. So we have to simplify everything. So when we get the square root of 4, this is a perfect square. You should be able to know, okay, the square root of 4 is equal to 2. And the way that we can use this chart is I look first to see, is the number in my radicand any of these perfect squares? And if it is, well, my answer is just going to be the x, because I know the square root of x squared, since they're inverse operations, the square root and the square will cancel each other out, and it's just going to give me that number in the number underneath. So when I'm answering these, I'm hoping that they're all perfect squares, and if I see it's a perfect square, then the x is simply just my answer. So if I ask you what is the square root of 225, you should first look through this part of all of our x squares and see, do I see 225? Yes, I do. Since this is on my chart, I know it's a perfect square, and the square root of that is simply just going to be 15. All right, so that's what we're hoping for. However, not every single question will be that easy. What we will be doing is learning how to simplify numbers that are not perfect squares. So in this case, I had the square root of 8. All right, if we were to type the square root of 8 in our calculator, this is approximately going to be equal to 2.8. So that's its actual value, 2.8. It's not a perfect square because it does not give me a whole number. And I can tell it's not a perfect square because I don't see 8 in any of these x squares. So I know all these x squares are the perfect squares I'm going to be focusing on. And obviously there's more perfect squares because we can continue with 16 and 17 and so on, but we're only going to focus up until 15 about. All right, so when I see it's not a perfect square, what I need to do is I need to ask myself, can any of my perfect squares go into my square root? Meaning, can I divide any of my perfect squares by these numbers? So can I divide 8 by 4? Can I divide 8 by 9? Can I divide 8 by 16 and get a whole number in return, and so on? Once the number is more than half of the number in my radicand or my radicand, I don't have to worry about that anymore because once it's more than half, it can't go into it a whole time anymore. So in this question, I actually wouldn't even look and see can 9 through 225 go into 8 because they're all more than 8. So I'm asking, can any of a perfect square divide evenly into my radicand? And yes, 4 can. So I can rewrite 8 as 4 times 2. You all agree that 4 times 2 gives me 8. So whether I write it as 8 or I write it as 4 times 2, I can substitute. They're one and the same. Once I do this, I'm then going to separate my radicals. And I'm going to look at them as their own individual radical. The square root of 4 times the square root of 2. And then the number that I was dividing into it, I know that's a perfect square, so I can simplify or reduce this. The square root of 4 I know is going to give me 2. So this gives me 2 as an answer. And it's still being multiplied by the square root of 2, which I can't reduce anymore. There's no perfect square that can divide evenly into 2. So this can be rewritten as 2 times the square root of 2. And if you plug this into your calculator, it gives me 2.8. So you see, it doesn't change the value of what I started with, but it's rewriting it in its most simplest form. So when we're trying to simplify radicals that are not perfect squares, we're trying to see, are there any perfect squares that are embedded into that number? Meaning I can divide that number by the perfect square, and then I can reduce it. So I can rewrite the square root of 8 as 2 times the square root of 2 because 4 times 2 gives me 8. The square root of 4 is 2. So since I couldn't take the square root of 2 as a whole number, it stays inside of the radical, and I just rewrite it as 2 times the square root of 2. And they are the same value. All right, we're going to go ahead and do a few different examples like this, always using this chart to help us along the way. All right, so we're asked to simplify this radical, the square root of 75. The first thing we do is we look in our perfect squares. Do I see 75? That's what we're hoping for. I don't. So I know this isn't a perfect square then based on my chart. Then what I do is I look and see, well, can any of my perfect squares divide evenly into this? Well, 4 can't, 9 can't, 16 can't, 25 can, 36 can't. Once I get to 49, I'm not even going to check any of the rest because 49 is more than half of 75. And at that point, I know it's not going to go into it as a perfect square anymore. So I'm just going to go ahead and stop there and stop checking. All right, now 25 went into it. So now I'm asking myself, okay, well, 25 times what gives me 75? And I can rewrite that as 25 times 3. So remember, our goal was to see, can any of these perfect squares go into that number? Once I identify that, I'm going to look at them as their own square roots. And remember, these are being multiplied. Square root of 25 times the square root of 3. Well, the square root of 25 based on my chart is 5, so I can rewrite this and simplify it as 5. And since I know that 3 is not a perfect square, I can't take the square root of it with getting a whole number. That's going to remain inside of its radical, and this is now 5 times the square root of 3. So the square root of 75 is equal to 5 times the square root of 3. They're the same numerical value. If we plug it into our calculator, it'll give us the same exact value, and that value is going to be around 8.7. So no matter what, it's not changing the value of my number. It's just rewriting it in its simplest form. Just like when we're adding fractions and we're trying to get like denominators. Well, when I multiply this by 2 over 2, and I get 2/4 plus 3/4, both times this is equal to 1/2 or 0.5. We're not changing the value of it. We're just manipulating or rewriting it so that we can actually perform the computation that's there. So the same thing, we're not changing the value of this square root or of this radical. We're just rewriting it in its most simplest form. Right? So the square root of 75 is equal to 5 times the square root of 3. All right, so our next one, the square root of 45. All right, now I look, hoping, is it a perfect square? No, it's not. So now when it's not a perfect square, I'm going to look at all my perfect squares and say, well, which one of these, if any, divide evenly into 45? Well, 4 doesn't, 9 does, 16 doesn't, 25 doesn't. I'm not going to test any of the others because 25 is more than half 45, so none of the others are going to go into it evenly either. So now 9 is the only one it does. So now I ask myself, 9 times what gives me 45? So it'll be 9 times 5. Once I do that, I'm now going to separate them and look at them as their own radical, remembering that they're getting multiplied in between. So the square root of 9 is equal to 3. So I can rewrite this as 3, and since I can't take the square root of 5 because it's not a perfect square, and no other perfect square can divide evenly into 5, it stays inside of its radical. So the square root of 45 is equal to 3 times the square root of 5, and that is simplifying it as much as we possibly can. All right, so our goal, step 1, is it a perfect square? Okay, it's not. So now, can any of our perfect squares divide evenly into our number? So our step 1 is it a perfect square? Step 2, can any of our perfect squares divide evenly into our radicand? All right, so that's what we're looking to do every time. Okay, now our example 3 is going to get a little bit harder, and then our example 4 is going to add one more little wrinkle to it, and then that'll be it for this video. All right, so now let's go ahead and do the square root of 72. Once again, we're hoping, do any of our perfect squares divide evenly into it? No. All right, so that means we have to simplify. So now I'm going to go through my numbers again. Can 4 go into 72? Yes, it can. And you will be allowed to use a calculator. However, you must show me every step. If you just give me an answer, I'm just assuming that you just plugged it into the calculator and that's what it was. So all these steps I'm showing you, where you're showing me, like I'll point it out here, but all these steps need to be shown. Right? 4 does divide evenly into 72. Does 9 divide evenly into 72? Yes, it does. 9 divides evenly into 72. Does 16 divide evenly into 72? It does not. Does 25 divide evenly into 72? It does not. Does 36? Yes, that does. Does 49? No. And that's more than half, so I don't need to check the rest. Right now, when you have multiple numbers that do divide evenly into it, you want to take the largest number. Right? If you take 4 or 9, you won't simplify it completely. You will only simplify it a little bit. So we would take the largest number. And also, once we see that we have multiple numbers that divide evenly into it, those two numbers multiplied together will always go into it as well. So when I see 4 and 9 go into it, I know 36 is going to, because those two numbers being multiplied will go into that number as well. But if you have multiple numbers, you take the largest number that can. So in this case, we will rewrite this then as 36 times what gives me 72? And 36 times 2 does. Then we're going to separate them. 36 times the square root of 2. And the square root of 36 I know is equal to 6. I can't take the square root of 2. I can't take the square root of 2 as a whole number, so it's going to remain. So this will be 6 times the square root of 2. All right, so just like we have to simplify our fractions as much as we can, we have to simplify our radicals as much as we can. If you were to stop and say, okay, 4, and say, well, 4 goes into 72, and it goes into it 18 times. We could rewrite this as 4 times 18, and then we could take the square root of 4 times the square root of 18. This is giving me 2, and this is going to give me the square root of 18. However, 9 still goes into 18. So this can be reduced even more. So if you don't take the largest number that goes into it, you would have simplified the radical, but not all the way. So that would actually just be considered AP and not proficient. All right. When you're taking your test, you must show me all of these steps. If you do not show me these steps, you are not going to get any credit whatsoever. All right. Unless I can find calculators that don't do the square root for you. But even so, I want you to show me all of your work. All right, because your calculators just go straight from the square root of 72 to the answer. So I need to make sure that you know how to do this and not just your calculator. All right, there's one more question we're going to go through, and that is it for this video. All right, so before we go through a fourth example, I just want to go through one first using a perfect square. So remember, I told you that when we write numbers really big next to that radical, these are not the same. So you need to make sure that you're doing the correct job of writing. If you meant to say this as an index, you got to write it nice and small here. When we write it big like this out front, we're saying it's 3 times that square root. So we're saying 3 times the square root of 16. So we would focus on and saying, well, what is the square root of 16? I know it's 4. So then we're saying, well, 3 times 4 is equal to 12. So we would actually have to multiply this number out front. When it's written like this, we're taking the cubed root of 16, which is completely different. All right, so when you're writing this, make sure you get in the habit of writing that number nice and small if it is an index, or writing it nice and big if we are multiplying. All right, but when we have that number out front, we're multiplying it to that radical. And since the square root of 16 is 4 and they're interchangeable, I can rewrite it as 3 times 4 and give me 12 as my answer. All right, so that same step and thought process and logic is what we're going to now apply to our fourth example. All right, once again, when that number is written nice and large next to it, we are saying 2 times that square root of 200. All right, so that 2 is being multiplied to that radical for whatever its value it's equal to. So when we have this, the first thing we want to do is we want to simplify the radical as much as we can so that we can multiply the 2 to it, to whatever we can. All right, so I look, is 200 a perfect square? No, it's not. All right, so now I got to see, can I reduce or simplify? Well, does 4 go into 200? Yes, it does. Does 25 go? Does 9? No. Does 16? No. Does 25? Yes. Does 36? No. Whoops, wrong one. Does 36? No. Does 49? No. Does 64? No. 81? No. 100? Yes. And then the rest don't. All right, and because 100 is halfway, so we don't have to check the rest of them. So when there's multiple, I take the larger. So that means I'm going to take 100, and 100 goes into 200 two times. So I can rewrite this as 100 times 2. All right, so now I'm going to separate my radical. So it's 2 times the square root of 100 times the square root of 2. Well, I know the square root of 100 is 10 based on my chart, and I know 10 squared is giving me 100. So this is being multiplied to our 2. So it's 2 times 10 times the square root of 2. So now, since these are now whole numbers, I can multiply them. Well, 2 times 10 gives me 20. So this will give me 20 times the square root of 2. So anytime that there's a number out front that's being multiplied, when you reduce or simplify your radical, you must multiply the number that was already there with your simplified radical as well. So 2 times the square root of 200 is equal to 20 times the square root of 2. All right, that is it for this video.